Now it's reordered. Yeah. So, so the questions that we are interested in answering today, right? So we are not going to see so much new stuff, okay? But so there's this part 2 of bifurcation diagrams over here. Okay, here it is. And the questions that we are interested in, it's small, right? But then I'm talking here. Yeah, let me invert this, maybe. This one? Like this. Yeah, better, right, better. So the questions that we are interested in answer today is the following, okay? So, okay, you have a system that you more or less know something about it, right? So for instance, we are going back to our Rosenzweig-McArthur model. I'm not sure if you are already tired, bored by it, I don't know. Yeah, because we have analyzed it so much already. But then, look, we know that this system can have extinction of the consumer. We know that there can be a stable fixed point. We know there can be oscillations. And by now, we already know that there's not much else that can happen, right? Yeah, or are not too convinced by that? I don't know, right? So the question then is, okay, but we had this, let me run this here already. Yeah, so we had this first plot here, and we had this bifurcation diagram on the carrying capacity. Let me plot this one here. Okay, it will take some time. Yeah, it's. Huh. Ah, when I hit enter, it cancels. Okay, it wasn't running anything at all, right? And the question that you may have, and that I think some of you probably have, is the following: how much of the results that we have is strongly dependent on, well, of choosing, because when I do a bifurcation diagram numerically, as we have seen here, right, we have to choose a lot of parameters, right? So there, in the system, we have 6 parameters, okay? So we are doing bifurcation diagram on one of them, the carrying capacity, and the other 5 I fixed, right? So there's this question, and then there's the second question. Well, what is so special about carrying capacity, about K, right? Maybe if I had chosen a different parameter, I wouldn't have seen cycles at all. I would have seen nothing. I don't know. Does that? You see what I mean? So maybe if in my own problems I choose the wrong parameter somehow, I'm not going to see what the system has. Yeah. So this is, I think, a reasonable fear, perhaps. Yes or no? Yeah. Yeah. So maybe we are not really seeing everything that the system has, just because I chose the wrong parameter values, or I did a bifurcation diagram on the wrong parameter. I don't know, right? Yeah? Yeah, do you? Yeah? And this would justify maybe going for a more refined analysis, analytical fixed points, and so on, right? But then what I want to do now, right? So is this, I always type an extra, when I hit Shift Enter, I always hit this button here, yeah. Okay, so here it is. So this is our original bifurcation diagram of the, so you remember this, right? So do I need to go over this again or not? So this is the Rosenzweig-McArthur, okay? And this is, I just run it with the same parameters that we had before. So R equals 1, K is 10, A is 1, H01, E01, and G01, right? So these are these parameters over here, okay? So the death rate of the consumer, efficiency, handling time, and so on, right? And this is a single solution, okay, where I have stable fixed point, and now I change K exactly as I did before, right? So we had this plot over here. You remember this one, right? Yeah? So I have extinction here of the predator, then fixed point of existence, and then this bifurcation to periodic solutions, right? To cycles. Okay. Now, what if I chose another different parameter, okay? Yeah, what would happen? Yeah, so I will choose A, for instance, okay? So I'm going to go here and look at different values of A instead of K, okay? Yeah? So so here I pretty much copy and paste the code, okay? But now I have a range of values of A, right? So I had 1 before, so I'm going to go from 0.1 up to 3, okay? And then everything else is exactly the same. You see, I only change it now that now I fixed K, and now I change A inside the loop, okay? And everything else is the same, okay? And at the end, I plot as a function of the values of A, right? The minimum and maximum, okay? And what does this look like? Looks like this, okay? So for a small a, I have extinction of the consumer, then I have a stable fixed point, and then I have cycles. You see? So actually our our first attempt varying K, doing a bifurcation diagram on K, was not so special after all, right? Yeah? Right, so now it's time for work, right? For you to work. So how was it? I'm not sure how you say this in English, but if you can do 1, you can do 10, right? Yeah? Yeah? Right, so now it's for you to, let's do the following exercise. We are going to do a bifurcation diagram on every parameter in this equation, just to see what it looks like. Yeah, does that sound interesting? Yeah? Yeah? Okay, so this should be quick, right? This should be quick. It's pretty much copy and paste, change the parameter values. There's some, you have to think a little bit about the range of parameters. Maybe you have to try it twice and so on, right? You don't need to have a lot of, it doesn't need to take too long. It maybe, I know, something like 50 points. At most 100 points in the bifurcation diagram is okay. Okay, and now I'm asking you to do it on H, on E, on G, and on R, right? And of course, if you want additional challenge, you can try to think ahead. What do you expect each of those plots to look like? Huh? Yeah, so this is a hard question, okay? This is, but maybe if you don't know how to answer that, just run the simulation, do the bifurcation, and then, yeah, and then you know the answer, yeah? Okay, so time to work. Let's go. So, 4 bifurcation diagrams. Anyone has questions before we start? Yeah. Okay, later. General questions? No. So let me pause. Yeah. So let's see the solutions then. So let me look at this. So I won't go over the details. So we already had the one for K, right? It looked like this. The one for A looked like this. Okay? You see that you always have to take the initial value, the A that was in the original equation, and play a bit with the range, right? Yeah? Play a bit with the range. You start with some range, and then you say, okay, here it is already extinct, so I don't need to go over this region. I can go to the other side, and then go a bit over on the other side, and maybe look into more detail in some region, right? Okay, so the bifurcation on H looks like this. So there's a region here for large H. So remember that large H. What does that mean, right? So H is handling time. It's the time that takes for the predator to consume each prey. Okay, so if it is large, then the predator cannot consume too much, and it ends up being extinct, right? So this is for large H here, right? So when I first did this, I went with H up to 2, right? And then I just said, okay, I don't need this region in the right here because there's nothing happening, okay? So I just stop at 1. 1 is already extinction, so I don't need to see anything else, right? I know that for any H larger than this, it's always going to be consumer extinct, prey, resource at the carrying capacity here at 10, right? No fun in that. But then, for smaller values, right? As you decrease the value of H, you have initially a fixed point of resistance between predator and prey, and then around here we start to see oscillations. Okay, then there's this valley here, then oscillations start to decrease in amplitude until you have once again fixed points, okay, stable fixed points. Yeah? So it's kind of funny here that in reverse, right? So, but this is possible with some parameters, right? So in reverse, the thing like you can go from fixed point to oscillations and then back to fixed points, right? Yeah, so this is something that happens, right? Why exactly? Well, this is a bit more complicated, okay? But then I have some intuition about this, but it's not the point right now to go into all of the details of the Rosenthal-MacArthur model, okay? I just want to illustrate what happens, right? So what can happen, okay? So E now, the E, remember that this is the efficiency of conversion from resource to consumer, okay? And if you do this, you look at plots like this, right? So you have, for very small conversion efficiency, you have extinction of the consumer again. Then it has a large region here with resistance, okay, with both of them. And then for some value here around half, more or less, you have, once again, bifurcation to oscillatory solutions. Yeah? Okay, so everyone okay with that so far? Again, if we want to know why exactly, we have to really look into the equations and look into the what are the mechanisms that generate the cycles and so on, okay? But that's not the point here. The point is, and I think it's pretty clear by now, that bifurcation diagram, okay, was not special at all, right? So you see this transition from fixed points to cycles on pretty much any parameter that you chose, right? Yeah? So it's like, why did I use K? Why I use carrying capacity in the first example? Well, because, you know, Roberto always likes to talk about the paradox of enrichment, and it's an interesting phenomenon, so let's do the carrying capacity, right? Yeah? Just because it makes for a nice story, you see? So it's not it's not only the way to find the, you know, you would see similar bifurcations on pretty much all the parameters, okay? Yeah? Okay, now going on here with G, right? So G is the mortality rate of the consumer, right? And if I run this, I get something like this. Here I didn't explore very well this region here, right? I think I was already a bit tired by now. And I left this whole region that is useless, right, after the, right? So I would probably have stopped at 0.6 here and then put more detail into this. So you see that there is a bifurcation here for very small values of G, right? So we also have cycles over here. When G is small, then the consumer can have a larger population and so on, right? And in the middle here you have stable fixed points, yeah? And finally R, right? So R is the one that I usually set to 1 right away, right? Because, oh, well, it defines the time scale and so on, right? And this is the one parameter where you don't see bifurcation to cycles, okay? This is the one parameter that you don't and you won't find bifurcations to cycles, yeah? So what ends up happening here is that as you increase R, as you increase productivity of the resource, the resource keeps the same biomass more or less, right? The same population value, and the population of the consumer just increases and increases and increases, right? So so it's kind of all this productivity is transferred to the other trophic level, yeah? And you don't see oscillations at all, right? So air by itself doesn't produce these oscillations, okay? So this is the only parameter that you wouldn't see oscillations at all if you did bifurcation diagram on that, yeah? Yes? First, well, he's first, sorry.
So my graph was basically the same as yours, but in the beginning there were oscillations.
Yeah?
Yeah.
You have oscillations? Oh,
like that, yeah.
Then even what I just told you is wrong? Oh, that's so bad. Yeah, so it's possible to find oscillations changing air. Let's go back over this. Okay, so maybe I have to run all of this again. I didn't find it originally. But then maybe I didn't explore as carefully as I could, right? So, okay, so this is the same, but then let's go for very small values over here. Yeah? Maybe not so much. Yeah, I'm doing the, well, it takes a while to start this stuff here. Yeah, so this is the region, all right? So let's run this. Okay, so, we're going to see problems. Yeah, well. Yeah, more about this in a moment, but then let's, yeah, sorry. So let's try this and see if we, yeah, no, stop. You see, when you look at this, right, you know that there's a problem, right? So there are two things here. Plot is very weird, and there is this error, this warning message, okay? I will talk about this in a moment, okay? But then let's just see what he's showing us, right? So before going into that, okay. Okay, no warning now, and then now, yeah, we do have this bifurcation here, but then it gets really weird. And I don't have any warnings, huh? Yeah, no warnings, but then this looks like an issue of small time. Maybe I should, what is that? What is T over here? So let's, yeah, okay, let me use this here. I think I was using short time, okay, so, where is it? Yeah, and then, let me increase it here just so do we need to go up to, no, we can stop earlier, yeah, maybe control here. Okay. Well, I already have a warning here, so it's going to be a mess again. Yeah, mess. Oof. Hard. Okay, hard. I will talk about this. So, I will talk about this kind of error in a bit, right? But then, yeah, I was wrong, right? So even with error, we also have this bifurcation for low values of error, right? So I think I didn't find it because usually what I expect is that for low values of error, you have extinction of the consumer before you have these oscillations. But for parameter, I think for G equal to 0, 1, we didn't see this issue. Okay, yeah, but it's a bit harder to find. Yeah, nice. Good job. Yeah. Next question. No? Ah, it was the same? Ah, okay, good. So you found something that I didn't find before. Nice. Okay, so far so good. So there are some issues, right? So you saw real life, how it is, right? You run with you try some parameters, and then there's this funny plot. But before I go into this, right? So message here, right? Message here is that when you have a certain kind of behavior in your system, right? You have oscillations, you have certain fixed points that are going to be stable, become unstable, and so on, okay? It's very rare that you will only find that region varying the correct parameter, okay? Usually, you see here, we find fixed points, stable fixed points, periodic solutions, and so on, exploring all of the parameters, okay? So key determined capacity was not a special choice, right? So you can more or less trust in your own models. That's okay, maybe it's nice to explore more than a single parameter, but you don't have to fear that, okay, I completely miss something about the model because one of the parameters and fits at that, okay? This usually doesn't happen, okay? This is quite rare unless you choose some extreme values of the parameters, right? Like, well, of course, if I take this model and choose some value of the mortality that consumer always was extinct, then it has no fun, right? So, yeah, okay, always extinction. But other than that, usually you are going to find more or less the stuff that happens in your model changing just a few parameters. You don't have to change all of them. You don't need to You see what I mean? So yeah, yeah. So you can this we did for this specific model, but this is very general, right? So it's very rare to find a system where there is some specific region that you only find if you change exactly this parameter in that condition. No, usually stuff happens in general, right? So for many different sets of parameters and so on, okay? Okay, good. So now the second part, and then I will use this to discuss these numerical errors here. Okay, the second part of the thing here is, okay, but what I did was, okay, I had a specific set of values of the parameters, okay? And then you can say, well, the professor he knows already what are the best values of the parameters, he has this already all worked out, and so what if I use a different parameter values, okay? Yeah? Does the choice of parameter also influence strongly the bifurcation diagram? The answer is that it could, but most of the time it doesn't, okay? Most of the time it doesn't. And if you think it may be happening in your system, just do the bifurcation diagram again with some other value of the parameter, okay? It's not that difficult, you know? So here we are going to look at, for instance, the same bifurcation in carrying capacity, but now choosing a large value of h, right? So what I call a large value of h here is with h equals to 0.8, right? So if you, now that we had done the bifurcation on all of them, right? I know now that 0.8 is large, but not large enough to go to extinction, okay? Yeah, so a large value of h, but it's still in the range where there is resistance, okay? And are we going to see cycles here on k as well, right? So this is the question. So I have the same setup as before. So so you see here that I have a range of k's from 0.5 to 20. I look this here, the parameters, the only change I did here is that h now is 0.8, okay? I run this stuff here, and you see this warning, right? This warning, okay? And then we plot the graph, and we will see some stuff that doesn't look right, okay? Doesn't look right, yeah? This doesn't look right, okay? And this coincides with this warning, so what does that mean, right? So let's talk about this kind of stuff first, right? So remember then, let's go back to the theoretical part of the class, right? So remember what I told you before, that when the first class on integrating differential equations, okay? We had that the int, right, our nice function, it does something nice that if you have your solution here, okay? You have x as a function of t, and your solution is going very smoothly here, right? So in this region of the solution, our numerical integrator internally, it knows that the solution is very smooth, it's changing very slowly, it's almost a straight line. And what can it do to increase efficiency and take large time steps internally, right? You remember all that story about the length of the time step of the integrator, yeah? That if we had a small time step, I can have a high precision, high accuracy, and if I increase the time step, I have a lower accuracy, okay? Okay, then we want to keep the solution accurate, but then we can also want efficiency, okay? So I can increase the time step when the solution changes slowly, and I have to decrease the time step when the solution changes rapidly, okay? The problem usually happens when you have solutions that have something like it goes very smooth for a time, and then suddenly it has a very weak oscillation, okay? So you have solutions that look like this, and then it goes back to smooth, and then, right? So you have this kind of solution, right? Where the transition between is smoother and faster. The difference in time scales in this region is very large, okay? So this is this is usually this sometimes leads to numerical errors. Okay, this is very common, appears in many different systems. And what are the practical solution for this? Okay, the practical solution for this is telling your numerical integrator, is telling the function OGEINT to work harder. Yeah, to work harder. Okay, so there are essentially two parameters that tells it to work harder. Okay, one is, should I put this into the tutorial or maybe in the, well, let me write here. One of them is MS step. So this tells me, this tells the function how many times, because at each step it can either increase or decrease the length of the time step, right? And this tells how many times you can do this in each time step, okay? So this is usually of the order, I don't know if the default value is 50 or 100. You can just go there and tell that MS step is now 1,000,000, okay? And see if it works. Another way to do this is another parameter, optional parameter that is called HMAX, okay? HMAX tells the following to the function. It tells the function that the maximum time step that it can ever do is this value, okay? So, okay, for instance, suppose that this is 0, 1, 2, 3, 4, something like this, right? So in this region here, maybe the program is attempted to give time steps of size 2 or 3, I don't know, something like that, right? But in this region here, it should take at most something like 0.1, right? Yeah, it should have a much smaller time step, okay? So I can go to my program and tell it that HMAX is going to be 0, 1, right? So it's always forced to increase the time step to at most 0.1. So when it reaches this region, it's going to be okay, right? Of course, both of these parameters have a side effect that it makes our program slower, right? Because it needs to do more work, okay? But well, that's life, right? So yeah. Okay, so let's see if this stuff here helps, right? So I see this stuff here. It happened here. Okay, so just go back here. You're not seeing. Yeah. So let's. Okay, back here. Okay, so let's go here, and I had commented here something that I think I tested this and it worked. Okay, so I increased MS step to 100,000 and HMAX to 0.1. Okay, and when I run this again, you notice that it takes a little bit longer, or maybe quite a bit longer. I don't know. And now there's no warning, okay? There's no warning, and the plot doesn't have those funny things over here. Yeah? How do I know which values exactly I have to set for HMAX or MS step and so on? Try and error, okay? Try and error. There's no general recipe for, yeah, so just try to set an HMAX for some value and see what happens, okay? So there's no okay, does that look reasonable? Yeah. So let's go back now for just to see that I'm not cheating, right? So this is I didn't know about the bifurcation on air before, right? That had this problem here. Let's see if it works, right? So real emotion, okay? Yeah. Without let's see if the recipe here is going to be enough, right? So I have the OGEINT here. I will increase the maximum number of steps to 100,000 and HMAX to 0, 1, right? So the same as before. This is a guess, right? But and run this again and see if I should have warnings and funny graphics. It will take longer usually. Suspense. Yeah? No warnings, no warnings. And now the curve is smooth. Yeah? Yeah? Nice, huh? Nice? Nice. Okay, so I'm lucky today. Yeah, I'm lucky. Yeah? It's always nice when, yeah, okay. So now the next exercise for you, okay? So now the exercise for you is do the same differentiation on k here, but now for small a, okay? For small a. Okay, can you do this quickly? Yeah? Come on, 5 minutes. Let me start here again. So let's see what the solution looks like, right? So I kind of I've thrown to you some little trick over there, okay? A little trick. So what do you do, right? So you just go here, you take exactly the same code as before, right? For the k over here, and you just change h batch point 1 and h point 1, okay? And then you just run it again and plot again, right? Oops. Oh, yeah, the plot is, no, sorry. Yeah, a over here, yeah, and the plot is here, okay? And this is the plot, okay? But then, yeah, confused you because I showed you this plot over here, right? What is the difference? Well, you see, you have here, what do you see here? You see dash of the consumer and then visit point, right, for small a. But now there should be something else to the right-hand side here, okay? So what do? You just try it for larger values of k, okay? So you see there's nothing interesting before k equal to 10, right? Because this is just extinction of the consumer, okay? So I start my range of k's at 10, and then I try to go for much higher values of carrying capacity, okay? Maybe in steps of 1, okay? So I run this again. Maybe I should use, yeah, it takes some time. Today is the day of long running times, yeah. Right, so I kind of tricked you, right? Yeah? Because, you see, it looks like it's different, but then the scale of the range of parameters that you want to look at to get the same plot is different. Right? Now, if you go for carrying capacity up to 100, then it's looking better, but there's still no oscillations, right? Maybe I have to go even further. Okay, so maybe let's go for 200, and I'll put a very large time step here because I want to be weak. Okay. Maybe today is the day we reach Google's limit on time, computation time. I don't know. Yeah. And here it is, right? So you see, we are looking just at this region here, okay? Up to 25 or 20. The first plot that we made was this very small region in the corner here. If we want to over oscillations again, I have to go to very large values of k. Okay, so what did this small a change? So it just changed a from 1 to 0.1, right? So the bifurcation diagram still looks the same, but now you have to have a range of, so I divided a by 10. I had now to increase the range of values of k, multiplying it by 10 also. Yeah, so you see the scale of a and k are proportional, yeah? You see what I mean? Does that make sense? So you see, the plot of the bifurcation diagram of one parameter does depend on the other, but in this case, it's, you see, if you look at this plot, it looks exactly as at what we had before, right? And this is again a trick on you because I know that it is exactly the same, right? It's if you dimensionalize in terms of k, the new a is just a over k, right? So it's exactly the same plot on a different scale, okay? Yeah. Someone wants to say something? Questions, comments? No? Okay, because I'm hearing some, yeah, okay. So you see, sometimes it does change, but sometimes it just changes in a trivial way, right? So this is a trivial way, I just change it. Now instead of having carrying capacity from until 20, I have to do it to 200, okay? But the figure is pretty much the same. Okay, are you happy with this? Yeah? Yeah, so you see, there is a possible impact of one parameter change in the bifurcation diagram of the other, but sometimes it doesn't matter too much, or it just changes the ranges that you have to look at and so on. Okay, so this is not something that you should worry about too much. Okay, good questions, comments. Yeah. Okay. So now let's do something more challenging. Okay, more challenging. So now what I want to do is, and now I'm going to teach a little finally. Okay, I was trying not to teach too much during this whole class. Okay, but now I'm going to teach a bit, because I know for this system that there are two parameters that are very closely linked together. Okay, and these are the parameters of attack rate and handling time, okay, because they are both involved in the functional response, right? And they kind of act together, right? So one measures the saturation of the predation, that is the handling time, and the other how quickly you reach the saturation. So they kind of go together, okay? I don't actually need this, right? So what I'm going to do now is look at bifurcations on two parameters, okay? So, or more precisely, I want to see how, what is the, so we see now that we have three regimes here, right? So we have extinction of the consumer, or coexistence in a stable fixed point, or periodic solutions. I have three possibilities of the final outcomes of this model, okay? I want to see how they change with two parameters, okay? But then an important distinction to do here, right, and that you have to be careful, is that it's not that you want to analyze the two parameters, right? If you want to analyze two parameters, you do a bifurcation diagram on the first, and then the bifurcation diagram on the second, okay? Why do you need the bifurcation on two parameters at the same time, right? Usually you do this not because you're exploring the two parameters, but because you want to investigate the impact of one parameter on the effect of the other, right? So you want to see the second order effect, so the impact of one parameter on the effect of the other, right? So it's, you see the difference, or is it clear the difference, yes or no? Yeah? The difference between studying the effect of two parameters versus the combined effect, or the effect of one parameter over the effect of the other, you see? So when you want this, then you have to do them together, okay? Okay, so it's not so common, this use, okay? This use is. It's very common to want to explore more than one parameter, not so common to want to investigate the impact of one parameter over the effect of the other, okay? Okay, so how do you do this, right? So this is done doing a heat map, an Euler plot again, okay? Now we have two parameters, so we have to use the plane, and we will color this plane, so this will be something like A in the x-axis, H in the y-axis, and each point in this plane will be a pair of values of A and H, right? And then we'll color each point with what? With a color corresponding to, oh, this corresponds to consumer extinction, or fixed point, or periodic solutions, okay? So just like we did in a previous class, you remember the color, the heat map class? Yeah? So the first thing here is to try to be able to classify solutions, okay? Good, yeah? So we want to look at a solution and tell in which of these three categories it falls into, okay? Right, so let's start then integrating this here, okay? And I'm already taking a very long time, okay, 5,000. And the first situation is with consumer extinction, right? So I put here a low value of k over here with k equal to 1 to see the extinction of the consumer, okay? You see this, right? Yeah? Okay, what happens with the value of the solution, right? So the consumer is going to 0. if I test the value of y, so let me print here the very last value here, okay? Y minus 1. Is it going to be 0 for the consumer? Oh, this is weird, right? It's inverted. It's consumer resource and not resource consumer. Oh, what did I do here? Now I'm confused. Yeah. 3 to minus 3 and 9. Sorry. Yeah. Thank you. Yeah. So I told this y1, right? So y is something that is something else, right? Sorry. Yeah. So I told this y1. Thank you. Yeah. y1. Okay. Now that makes sense, right? So this goes to 1, right? The resource goes to 1, and the consumer goes to 10 to minus a negative number, yeah, but 10 to minus 14. Right? So this is a very small number, but it's not exactly 0, okay? So I cannot check if this is equal to 0. I have to check that this is smaller than something small, okay? So then, what do? I take the last points, okay? I take the consumer, the second column, look at the last 10 points, take the maximum, okay? Because I cannot also check if the very last value is small, right? Because what could happen? It could happen that solutions oscillate, okay? And then, what if the predator does this, okay? And I have the bad luck at taking the last solution at exactly this value, right? So it would happen, right? It could be that there is a very small value of the predator, but it goes back again, right? So I have also to avoid this, okay? So what do? I take a certain range here. I take the maximum value in that range and see if that maximum value is still very, very small. Okay, yeah, does that make sense? Questions? Okay, so this is the test to see if the consumer really did go extinct. Okay, if it goes extinct, we know that we are in the region, I told this 1, right? Only the resource. Okay, now the second situation here is consumer resource in equilibrium. Okay, so if this, the previous one doesn't happen, what do I have to check here? Okay, so this is a larger k. I told this y2. I have to check that the solutions at the end here do not oscillate anymore. Okay, do not oscillate. So what do? I calculate the maximum and the minimum and check their difference, right? If they are very small, again, are they going to be 0? Well, there are oscillations here in the beginning, so maybe there are still very, very tiny oscillations along the solution later, okay? Maybe this doesn't go to exactly 0 again, right? So this is how I do it. So I tell the solution here y2, right? And I take the last 1000 values here, take the maximum, and subtract from the maximum, I subtract the minimum, right? So the maximum minus the minimum is the amplitude, okay? And when I run this, I get 10 to minus 6 for the resource and 10 to minus 7 for the consumer. Yes?
I got lost in the middle and I don't understand the purpose of this.
Okay, so the problem is the concept or with the code? The idea of amplitude is okay or not?
Can you repeat, please?
Okay, so let me go to the board. Maybe it's easier in the board. So the thing is like this. You have, if you have an oscillation solution, oscillatory solution over here, right? You have this for the resource and this for the. It doesn't matter. Just one. Okay. So this is C. I take a range of values over here. Okay. And then what is the amplitude? The amplitude is the difference between the largest value over here until the smallest value. Okay. So this is the amplitude. Okay. This is the amplitude, the difference between the maximum and the minimum, the peak and the valley, okay? Okay, so this is the amplitude. If this solution eventually goes to a a fixed point, okay, what happens? The minimum and the maximum here will be pretty much the same values, right? So I discard the beginning, right? I discard the beginning, look only at the points at the end of the solution, okay? And now here, in this region here, the maximum value minus the minimum value is very close to 0, okay? If this were a mathematical solution, right, this goes to 0, but it's just in the previous equation, we don't see exactly 0 when you do the numerical computation. You see some very small value instead, okay? Does that make sense? So the concept is clear. So what we do now is we take the maximum, the minimum, subtract them, and look at their values and check if they are very small, okay? So if they're very small, I'm probably in this region and not in an oscillatory solution, okay? Of course, it's hard to, okay, just at the bifurcation point, so we have seen plots that look like this, right? They go here, and they start to open like this, okay? Right at the bifurcation, you will have very, very small oscillations, okay? And then this point here, it will be a bit imprecise, okay? Because maybe you are counting something that is a very small oscillation, an oscillation of amplitude 10 to the minus 7, it's possible. Maybe there is a solution over here that is an oscillatory solution with very, very small amplitude. But we are going to ignore this because, yeah, there's a maximum precision here, okay? Good? Does that make sense? So there will be an issue with maybe counting something as a fixed point that should be an oscillation, but it's okay. It's only a very tiny region over here, okay? Very close to the bifurcation point, okay? Okay. And then the opposite also happens, sorry. Sometimes you are here, you are still in the region that is a fixed point, but here, very close to the bifurcation, it takes, instead of going quickly to the fixed point, you spend a very, very, very long time oscillating, okay? So sometimes you are taking some time here, you're throwing all of this out, but you still have oscillations here, and you may count this as an oscillatory solution, but if you waited long enough, this would be a fixed point, a stable fixed point, okay? So this error can go either way, right? So yeah, so it's, you know, getting exact solution here is complicated, but usually both cases happen only very close to the bifurcation, right? So it's not too bad, okay? Okay, so let's go back to our program. We now want to, so we now have to test this, right? So how do we test? In the previous case, we have just a number, okay? We had just a number here, right? In the y1 case, right? So I just have to check if this guy over here, yeah, I didn't run this. If this guy here is small enough, okay? So I would just check, well, is this smaller than, I don't know, 1 to 10 to minus 8, something like that. I don't know. True, right? I just test one number, okay? Yeah? But now, if I do this here, okay? If I do this here, and I test if this thing here is smaller than, I don't know, 10 to minus 5 here, okay? It doesn't give me a boolean, it gives me two values, true and true, okay? I want to say that this is a fixed point if both of them are true at the same time, right? So I call a function from NumPy called a logical AND, okay? So this is like this. This means this will be true if all of the values are true, okay? Oops. What did I do here? I don't know what I did wrong, sorry. Let's try this again. True and true, an array of truths. Okay. Yeah. Let me cheat again. I had the solution somewhere down here. Yeah, just a moment. Well, I'm not so sure what I did wrong over there. Ah, okay. Logical, yeah, I confused the two functions. So let me try to clarify that a bit. Where was I? Where was I? I was over here, yeah, on this area here. So maybe let me comment this and tell you the difference between these two functions. So logical AND takes two values and compare them, okay? So if I have two values, right? So it takes two vectors and returns two vectors, okay? Something like this. Okay, so I pass it two values and it returns the combination of the two, right? So two arrays, so true with true gives me true, right? And true with false gives me false, okay? This is logical AND, but what I wanted here is something called all, right? If I want all of them to be true, okay? So instead of using logic, because here I just passed a single array, right? I want all of the elements to be true, and this is not the logical AND, this is all, the all function that is, that now all of them are true, so this returns true, okay? Does that make sense? Yeah, they're a little bit different, okay? Good. And now what happens if the first one is false, right? So the consumer is not extinct and the population is not, the amplitude is not going to 0. Then I have oscillations, okay? So you fall into the third case, okay? Okay, so now I will write this as a function, right? So I receive a solution. Here I assume that y is already only the ending of the solution without the transient part. I check that the consumer maximum is smaller than some threshold here. If it is, then I return that, okay, this is consumer extinct, okay? So this is the situation with consumer extinction, yeah? And I return it 1. Now, if this is not the case, else if, then I look at the maximum, the amplitude, okay? This is the amplitude. And I check if the amplitude is smaller than 10 to minus 5, okay? If this is true, or if both of them are true, the all over here, I return 2. And if this is also false, so this is the stable equilibrium, okay? And if both of them are false, I have oscillations, okay? So this is H3 over here, okay? So this is what this function does. It receives the solution and tells me if this, in which of the three cases we are, okay? And now you see, so the third situation was with Y3 over here, you have consumer resource oscillations, okay? And now I'm going to check, I have, this is why I use it Y1, Y2, Y3, right? So I can get at the end here and use our function. The first case is classified as 1. You see a check regime that is this function. What did I pass to it? I pass Y1, the last 1,000 times steps, okay? And Y2, the last 1,000 times steps. Y3, the last 1,000 times steps. And identifies the first case as H1, the second as H2 correctly, okay? Nice? Does that make sense, people? Yeah? So I created a function to classify the solutions, okay? And now what do I want? I want to have that color map, okay? The color map, what do I have to do? I have to have a function that I pass the values of A and H of the two parameters, okay? So what do I have to do? I have to create a function that receives these two parameters, solves the differential equation, and then uses this function to classify the solution, okay? So I have this function called solve and classify that receives the two parameters, and now it takes the previous parameters and changes the values of A and H, solves it for a long time, then takes the solution and check which regime it falls into, okay, with the last 1,000 times steps, and returns this value here that should be 1, 2, or 3, Okay, so if we do this again, right, so now changing here, using solid classifier with A equal to 1 and H 0.1 or 0.5 or 1, right, so if we go back to our bifurcations on H, okay, 0.1 is here, 0.5 is here, 1 is over here, right, so I have stable fixed point, oscillations, consumer extinction, okay, and this should give me, yeah, 2 to 1, right? Fixed point, oscillations, consumer extinction. Yeah, nice? So far so good. And now we just follow the recipe from the other class. I create a grid with the values of A and H, right? And then run this function on each point and use the result to plot it, okay? So I have a range here of A's, from 0.01 to 1.6. I kind of guessed this a bit, okay? Values of H as well. I created this 2D grid with mesh grid, you remember that? Now X will contain the values of A and Y the values of H, okay? And then I use our function to run over all of them. Remember that I have to vectorize this function, okay? I vectorize this function first, and then I run this stuff here. And this takes quite a bit of time, okay? And finally, with the result, I will plot this in a color, in a heat map here, and hopefully, after this is done, I get a nice plot, okay? But this is the end of the class, right? But then let's wait. It didn't take as much time as I expected. Okay, nice. So you see that for small values of H, right, you have here extinction, okay? For small values of A, it doesn't matter much the values of H here, I always get extinction, okay? As I increase the values of A, now I have, for many values of H, I have fixed point. For some very small region here, maybe a single point actually, right, I have oscillations, okay? But as I increase A, then I start to have I don't have any more, it's harder to reach, you need a much higher value of H to have extinction, should be here, this region of extinction. And now I have a large region of oscillations for many values of H, right? So essentially, this part in yellow over here corresponds to the belly of the bifurcation diagram on H, okay? And I see that as I increase the value of A, I increase this belly in this plot here. Does that make sense? So here I don't have any belly at all, and here I have this whole region here. This is at 1, right? At A equals to 1, I have this large region where I have oscillations as I increase H from 0.1 up to 0.7. Yeah? So you see that in this case, I don't see just a straight line. I see that there's really a strong dependency between these two parameters, okay? As I increase A, I have this region in the middle of the region of stable existence. I see this region of oscillations also, okay? Nice? Okay, so interesting. I hope this is interesting, okay? So this is the way to do bifurcation plot, or maybe look at the different regions in terms of more than a single parameter, okay? Of course, this is not a very nice plot because it's too few points, right? But then if I go here, I can increase the number of points, decrease the time step, the steps here. But then this takes a long time to run, okay? But I didn't want to do this in the class, okay? Okay, people, so that's it for today. Yeah, I hope you feel now more confident to do bifurcation diagrams and trust your results, yeah, with how to play with that and so on in your own models, okay? Thank you.